My name is Daniel, and today I'm going to talk a bit about verified verification generation and verified compilation for Dafny. Now, if you look at the list of authors, you'll see this is spread across many institutes. The reason for this is that most of this work I've done as my master thesis at ETH Zurich, which was supervised by Magnus, Myreen at Chalmers, and during those 6 months, I spent 2 months in Singapore with Yong Kiam, who's also now my PhD supervisor as of today. So without further ado, but let's jump right into Dafny because I think there's lots of stuff to cover, which is very fun. So if you've worked with Dafny before, then this side should be very familiar to you in some sense. So it's because it's Dafny in VS Code. So what we have here is the McCarthy function. And if you look at the specification, the ensures is the post condition. And what it says that if you have an input which is at most 100, the result is 91, hence the name 91 function. And otherwise, it's n minus 10. It also has a decreases clause, which gives you the termination measure. This is something that needs to decrease on every recursive call, which ensures that Dafny knows that this function or this method actually terminates. And if you look at the body, you probably can't really see why this would implement the specification. I mean, that's fine. It's not a particularly useful function, except that it's a bit of a challenge. And the reason it's a challenge is that you see you have a recursive call, which we store the result in temp. And then we have another recursive call, which takes that as an input. So for the second call, we need to establish the decreases. But for that, we need to first establish the post condition of the first call. So you can't just go on naively, just trying to separate the termination measure from the post condition. Hence, it's a bit of a challenge. But Dafny can very nicely master this challenge, as you can see by this nice little green check mark there. But I'm not sure if you've ever asked yourself this, but what does this green check mark actually mean? And one answer we came up with is this theorem. If you take a look at it, in the assumption is if you have the compiler, which is the Dafny to CakeML compiler, which is verified, you pass it as input this method. It returns you a McCarthy CakeML compilation result. It could fail, but it won't. In this case, it won't, trust me. And then the conclusion is that essentially a Hoare triple on CakeML programs, which has already existed, which is that for all integers n, you have exactly the specification above, namely that if you pass this n to the CakeML function, it will return an integer, which is, if the input was at the most 100, it's 91, and otherwise it's n minus 10. So the rest of this talk, I will give you a bit more background on motivation on Dafny, followed by a brief tour exploring the pieces that go into building this theorem. And then we'll put all these pieces together, and then I'll talk a bit about future work. But let's first talk about what would this look like in Dafny if you forget about our project. So you write your Dafny program, and then you want to compile it and verify it. And these are 2 separate stages. And since Dafny doesn't have a native compiler, by default, it is translated or compiled to something like C# and Go. And then you can use those tool chains, C#, the Go compile to generate a binary that you can end up running. To verify it, Dafny is translated to something called Boogie, which is an intermediate language for verification. And then there's a tool called Boogie, which takes Boogie code and generates verification conditions. And then you can pass these verification conditions to an SMT solver, and that will give you a thumbs up or thumbs down on whether your program is correct or not. Now, the issue is that all of this is part of the trusted computing base. And this is a lot of non-trivial code. So even despite best efforts, bugs will happen. So this is a paper from 2024, which has shown a couple of previously unknown Dafny compiler bugs, some of which are soundness issues. So our project aims to alleviate this by essentially building this pipeline on foundations that are solid. And for that, we take a look at something that we call mini Dafny, which I think is a common name for subsets of Dafny, which is imperative. And then we first, for a verified compiler, we build a verified compiler from Dafny to CakeML. And then we can use the already verified CakeML compiler to generate a binary. Now, this is very similar to the original Dafny pathline. For verification purposes, we don't go to an intermediate language. Instead, we immediately generate verification conditions on Dafny. And then we take these verification conditions and manually prove them valid with tactics. And we don't do this because I think this is a good way of doing things. It's not. The reason we do it is as a sanity check to make sure that we don't produce false as a verification condition, because that's sound, of course, but it's also completely useless because you can never prove it valid, right? And all of this work has been done in the world's second best theorem prover, Hall 4, and it's foundationally verified. And what I mean by that, we have some AST, we have the semantics, and all the proofs and components have been verified with respect to that one semantics. OK, so let's talk a bit about the compiler. And first, let's talk about CakeML. So what is CakeML? So CakeML is a verified subset of standard ML. And that means it has a verified compiler with a bunch of intermediate languages, which go down to machine code. And it also has, a lexer parser, which is verified. And this is all great and fun. But more recently, the CakeML project has evolved into something bigger, and namely as an ecosystem of verified languages. And then CakeML is not a verified subset of standard ML, because really, who cares? I hope I didn't offend anyone with that. But really, you can see it as a very rich intermediate representation. And you have pure Cake, which is this Haskell-like language which compiles down to CakeML. And you have Scheme, as you've just seen. And then we have Dafny, which is what I'm talking about. And it's also a special language because it's a verification of our language. And there's also Pancake, which aims at the lower parts, and it's a systems programming language. And the reason I tell you this is because this opens up opportunities where you could, for example, imagine where you verify a program in Dafny, and then you can call it from pure Cake or from Pancake, or everyone can call everyone, and at the end of the day, you still have an end-to-end theorem that everything is correct down to the binary. OK. So now everyone knows what CakeML is. We can take a look at an example. And we'll just take a look at a single example. There's a lot to cover, which is variables. And variables in Dafny, you can declare them. You don't have to initialize them. And then you can assign to them. Now, if you know standard ML, you would probably think that we compile this to references, and you'd be absolutely right. But there is a wrinkle that we need to resolve, namely that references in CakeML always need to be initialized, where in Dafny they do not. And there's different things we could do. We could box them. We could use an option. We could just put none if it's not declared, not initialized, the declaration side, and otherwise put some. But that has the issue of being a boxing step, and we know that a valid Dafny program will always first assign and then read. So we would be wasting cycles for no good reason. So instead, we zero initialize it. And here I really mean zero initialize. So if you look very carefully, that's an integer, and then we assign true to it. So this program will not pass the CakeML type checker, and that's fine, because we have a proof which says, or a theorem that says, if you prove your Dafny program correct, the CakeML compiler, the Dafny to CakeML compiler, and then by extension the CakeML compiler, will only produce code that does not have undefined behavior. So this is OK. It might look weird, but it's OK. So, but how do we know that the Dafny to CakeML compiler is correct? And we know, well, to know that, we first need to define what it means to have a Dafny program, right? We first need to define semantics. And the way we define semantics is using functional big step semantics. Now, if you don't know what that means, I really want you to think of it as an interpreter which has a clock or fuel which makes sure that it always terminates. You can still write programs that diverge. It just needs to terminate so we can define it as a function in the logic. And then you can take a Dafny program, run it through the interpreter, and get a result. And then since CakeML also has the same kind of semantics defined, what you can then take is the Dafny program, compile it, pass it through the CakeML semantics, and also get a result. And then the proof essentially consists of proving that these are always equivalent. And the way we do this is using an induction that we get from defining the semantics. And then for each case, we just have to prove that they're equivalent. OK. That's all I wanted to say about the compiler. And we support a bunch of different. So one thing that we also support are, for example, early return. But I'm not going to talk about that in more detail, but instead move on to the verification condition generator. So, and for the verification condition generator, I want to start with essentially the workflow that we approach that you could actually probably use too, in case you wanted to write your own verified verification condition generator. So the first thing we did is define the weakest precondition calculus using inductive. And then we proved that it's sound. So we had sound rules. And since there are proof rules, we can't really execute them. So we need to define something like a executable function that can actually generate the weakest preconditions. And then we need to prove that this, this function that actually generates the weakest precondition does exactly what the proof rules do. And then we did this for mutually recursive function at the very beginning. And then we hit soundness issues. And then we just added side conditions where needed. And over time, we just added more and more rules. So we had a bigger and bigger subset. So it's a very nice workflow. I liked it a lot. So please do consider maybe using it for yourself. But here's an example of this proof rule. And it's a very simple example because there's a lot of components to it. You don't need to look at most of them. The most important ones are the ones at the top. So we have the weakest precondition. This ensures. We'll get to it in a second why that's ensures. then we have the statement, then we have the post condition, and then another post condition, which is the post condition on return. So as I alluded to earlier, we support early return. So if you have a statement, as a statement composition, you're not returning. That's different from when you're early returning. And when we go to the soundness statement, this difference will become a bit clearer, but just know there's two different kinds of post conditions. And since this is the proof rule, we can't run it, as I said. We need a function that you can run. And it's essentially the same as the proof rules, except that this thing, this weakest precondition, which is on the left of the statement, becomes the output, as you can see here, so the arrow. And one thing that I would like to mention here is this is a result monad. It's in R, it's just right. The reason is because the VCG can fail, and then it will, for example, return left with an error message saying, like, you're trying to assign something that you declared as a Boolean as an integer. But that's on the Dafny level. OK. So return is a very simple statement. And I'm sure if you know, it's maybe not very deep. But heaps are a bit more complicated. So what I have here, for example, is if you allocate an array, of an integer array of size 2, and you initialize the first element to be 67, you need to generate some weakest precondition. And it looks something like this. Now, you shouldn't get lost in all the text. But the key point is this for all heap, which is an expression that we added. And what it does, it quantifies over all heaps, allowing new allocations. And it also havocs everything that is in this list. So havocing means that it essentially forgets what the contents are, but the types are maintained. And if you now think, if we walk through this example very procedurally, suppose we're in some heap, then this for all, we hit this for all heap here. So now the heap is the same, except we may have new allocations. And then you can interpret this for all a array int as, OK, now assume you have an integer array of size 2, which concludes the allocation. And then for the update, what we have is the setpref. What setpref does is you can suppose, so what you can imagine is essentially remembering the current heap. Then you again havoc it. So you quantify over all heaps, forgetting the contents of A. You update 67, or you update the first element of the array of 67. But now, since you only updated the first element, you need to maintain that the rest of the array is unchanged. And that's why we set the heap before, because now we can use pref heap to refer to the previous values. So really, the key point here is we quantify over arrays, we quantify over heaps, we havoc some locations, and then we set we can set heaps to remember them and then refer to them using pref. And we can use the same thing for all expressions. And even though I showed you integer arrays of size 2, we also support arrays of ints and arrays of arrays of arrays of arrays of int. The only limitation being that the modifies clause, if you're familiar with Dafny in that sense, we only support it on variables. So if you're an array of an int, you cannot say you only modify the first element of the array, right? So that is a limitation. And then, as promised, the soundness statement. So what this says, if you're familiar with soundness statement, it's very intuitive. So it says if you have a proof, essentially, that for the precondition rex, you execute the statement, and then you have post and ensures. Well, then if you start in a state which satisfies the precondition, there exists a state and a return value such that executing a statement in the initial state that satisfies the precondition, you get some return value that is not a failure. It's either just continuing, like in the case of sequential composition, and or returning, which is this s-red stop, and then post and ensures holds accordingly. And if you're curious about where the termination is, it's hidden here. I'm not going to talk about more, but it's in there. We definitely have, this has a proof that everything terminates. And with that, we can put everything back together. So I've shown you the sketch of the compiler correctness. I've shown you the VP calculus soundness now. I haven't shown you that the verification condition generator is correct. That's a very simple lemma, and the proof is also relatively simple. And I also haven't shown you the validity of VCs. That's just whole forward tactic machinery. But if you put everything together, you can derive this beautiful theorem, which says that the CakeML binary has the exact same behavior as the Dafny code you gave it. And just to conclude, some bit of future work. So as I said, manual proofs with tactics is not fun. It's not the 90s anymore. We have SMT solvers. So it would be good to be able to translate our verification conditions down to SMT, and then pass this to an SMT solver. And maybe if we have an SMT checker, we can read in the proof and have some nice theorem about that. Another very obvious, I guess, future work is just support more features, like object-oriented and functional features. They're used in Dafny, so I think they would be important to make a realistic compiler. And then finally, what I alluded to earlier with this language interoperability, it would be cool to be able to call CakeML code freely. But in addition to language interoperability, it's about FFI. So Dafny itself doesn't give you any means to reason about input-output in the specification language. So it's a bit questionable how you should define the semantics. But CakeML has verified FFI, so you could imagine that maybe you could connect these two and get the best of both worlds. And with this, I'm done. I'm very happy to take any questions you have, and thank you for your attention.
We have plenty of time.
So maybe mini-Dafny came from earlier work, but can you say something about, have you kind of validated the relation of mini-Dafny to actual Dafny? Or is there maybe there's like some discrepancy that people could figure out, or how?
So if I understand correctly, you're asking the differences between mini-Dafny and Dafny, or?
Is it like a true subset, right? I mean, the problem is that Dafny itself is not formally defined, right? And so, I mean, arguably one who should kind of test if you really want to be sure that mini-Dafny does what real Dafny does. Right?
Okay. So we do have a couple of examples that we test where we just run our compiler and the Dafny compiler and check that the output is the same, just as a sanity check. There is a mismatch, and namely in the way we handle declarations. So whenever we hit the declarations, we suppose there's essentially like a block statement. So our variable declarations, so in Dafny, the way it works in Dafny, you can have like blocks, and that delineates a scope. We don't support that. We just have every declaration, is a scope, and then we don't care about any other scopes you do. That's like one difference. I don't think it's very deep. But other than that, I think it is a true subset, I think.
Among the nice things I've heard about Dafny is the capability to react gracefully in the case the specifications or the programs are wrong. To have good support for users. Do you think this support can also be the object of proofs?
So I'm not sure I fully understood the question.
You're doing a formal verification of the VCG.
Mm-hmm.
But this is for the case of where the programs where things work well.
Mm-hmm.
And is there something that could be said formally about the cases where things don't work well?
So I think what you maybe could do is there's parts of, so if you remember when I talked about variable declarations, we need that Dafny code is valid for it to generate compiler code that doesn't have undefined behavior. So maybe it is possible to pull out this type checking thing that is required for that into a separate pass, and then you get the guarantee that you have whatever you give to a Dafny, when you give Dafny code to our compiler, and if it passes this like first check, it still generates code that at least doesn't have undefined behavior at the end. But I'm not sure if there's anything else you can pull out. If that
more like counter examples.
No, I see. No, so we haven't thought about that at all.
There are some Dafny functions for which it doesn't make sense to compile them. I'm thinking about lemma function and things like that don't really have any kind of computational content. And I'm wondering if it's definitely out of scope of your approach, or you could modify your approach to handle this kind of function which you cannot compile meaningfully.
Okay, you've hit a point that I didn't mention. So we do sweep like Ghost a bit under the rug, so we don't handle it very concretely. But I think it's so a proper. We should do it. So we should recognize when something is Ghost, and then don't compile it, but still check it so it can be used in specification. But we don't support that yet. But I think that's more of like a proof engineering thing, and it's definitely doable, I think.
a similar question as the first one about the verification conditions. How did you establish what verification condition Dafny actually generates? And I think it's even a moving target that changes over versions, doesn't it?
So the verification conditions we generate are very much motivated by the soundness theorem. So I guess it's a maybe you, I'm not sure what you mean with the moving target. It's very much we have the precondition, run the body, get the post condition. So we don't particularly care about what kind of boogie code the Dafny produces. We have essentially our own thing. So we don't try to be compatible with boogie, if that's what you meant.
Yeah, well, my experience is that it is not always what you find in, for instance, the book of Lino. It does a few subtle things differently.
Yeah. So we don't test for that, but it would be good to test for that. I do agree. But if you have time, I would be curious to learn, like, what maybe I feel like you're thinking about some very specific solid case I'm curious about.
Yeah, sure. Let's thank our speaker again.